If you were absent, or if you just want to review over kinetic molecular theory, here we go. So the kinetic molecular theory, kinetic meaning energy of motion, molecular, molecules, and a theory. So a concept that has been scientifically tested dealing with the energy of motion of molecules. So this theory states that all matter is composed of atoms and molecules that are in constant motion, right, kinetic, move at random, and hold kinetic energy. The more energy a particle has, the more it will move, and the faster it will move. The more energy something has, it also depends on what state of matter it is in. So we start with a solid, which has the lowest energy. Molecules are held close together in a pattern where there is very little movement between them because they are tightly packed. So for water, I'll just draw a few of the molecules. You have O with two H's. O with two H's. O with two H's. And they're in a very strict pattern. Okay? So you can imagine an H down here and an H down here. Okay, if I was trying to draw solid water, also called ice. Now this is not a very good depiction, but it's hard to draw on the iPad. For popcorn, what my example was I had popcorn seeds inside butter. So if I have a whole block of butter, we'll consider this whole square to be a block of butter. My popcorn seeds are in perfect arranged shape. Now the reason why I use popcorn seeds is if you look at an ice cube, you can't actually see the molecules. So it's hard to really imagine them being in this perfect structure, whereas popcorn seeds in butter, you can visibly see them. So there will be our analogy for what's happening to the molecules. So this is my analogy for what they look like in a solid. Now if I add energy, okay, so going from a solid to a liquid, I add energy, okay, usually in the form of heat. So in this classroom, I took the butter with the popcorn seeds and I put it into a beaker and I put it on top of a hot plate. So I added energy. When you add energy, these molecules start to break apart from this rigid structure and they're free to move around. So the molecules slide past each other and they have more space to move than in the solids, but still less than the gases. So in my liquid example, I may have a water molecule. Well, this guy's upside down. He's going to slide that way. And I have another one over here. And he can slide that way. They're free to move, but they're still stuck in this container. Now for my popcorn seeds, as I melted it, right, my popcorn seeds were able to move around inside the beaker. If you shook it around, all the popcorn seeds flew all over the place inside the beaker. Okay. Now going from a liquid to a gas, once again, I have to add energy. Add, I'll just put an E, add energy. So as I continued to put both of these beakers on hot plates, well, with the water, I hope you know what happens when you add energy. It starts to boil and you start to see the steam, which is that liquid water becoming a gaseous water. So if you have one water molecule here, he's still stuck in the beaker, but we have plenty that bounce all the way out, and one guy ends up all the way over here. Okay. And you end up with another one. He comes all the way up here. How about? Okay, they're able to fit into whatever container they're in, which at this time it was the classroom, so the water molecules were able to go anywhere in the classroom. Now for my popcorn example, as I add energy, remember this is an analogy, as I add energy, my popcorn also pops out. It has a lot of energy, and my popcorn seeds go all over the place. So in a gas, my molecules move very fast at random patterns with varying amounts of distance between the particles. They have the most energy, They can expand or compress to fill any shape. So in this case, the shape was the classroom. If I opened the doors to my classrooms, the shape would be the entire school. If you open the door to the outside, the shape now becomes the world. Okay. Now this unit is the gas laws unit, so we're going to be specifically looking at the kinetic molecular theory of gases. So this theory consists of 5 postulates. Another word for postulates would be ideas or rules that describe the behavior of gases. The 5 postulates are: gas particles are of negligible size compared to the space between them. Negligible. I want to make sure that I'm going to underline some words throughout these. Part of your homework is to actually reword each one of these theories. You'll have to have all 5 memorized. So make sure you understand the words that I underline, because they're very crucial to understanding the theory. So gas particles are of negligible size compared to the space between them. The particles are in continuous, rapid, and random motion. Their collisions are elastic. There are no significant interactions among the particles of gases. And my 5th postulate ended up on the top of the page. When temperature increases for a gas, the kinetic energy of the particles increases. Temperature and kinetic energy. These are going to be some very critical concepts for you to understand. So let's look at the definition of temperature. Temperature is a property of matter which reflects the quantity of energy of motion of the particles. Quantity is an amount, and energy of motion is kinetic energy. So temperature is really how much kinetic energy does a particle have. So when you're saying that the room is cold, you're really saying, man, the atoms in this room have a very low amount of kinetic energy. However, if you say that in class, people might give you a weird look. Now, there are 3 different scales for temperature. We have the Fahrenheit scale, which is used in America, Celsius scale, which is used by the rest of the world, and the Kelvin scale, which is used in the science community. The Celsius scale is based on the freezing and boiling points of water. The freezing point of water is 0 degrees Celsius, and the boiling point is 100 degrees Celsius. Now, the Kelvin scale is based off the theory of absolute zero. This is the point in which you've taken away all the energy from an atom. If you take away all the energy from an atom, those electrons aren't able to keep orbiting the atom, and the atom actually collapses. So this theoretical number, it's something that's never actually been reached, is a negative 273 degrees Celsius. So in order to convert between degrees Celsius and Kelvin, you add or subtract 273. So I'll do a couple of these with you. Let's get rid of this. Okay. So going from 100 degrees Celsius to Kelvin, you always write what you're given, and then you're either going to add or subtract 273. In this case, we're going to add 273. Look at the example up here. 0 degrees Celsius equals 273 degrees Kelvin. That means 1 degree Celsius equals 274 degrees Kelvin. 100 degrees Celsius equals 373 Kelvin. Make sure you have your unit. Now going from Kelvin to Celsius, 29 Kelvin plus or minus 273 equals a certain number of degrees Celsius. In this case, we're subtracting. Going from Kelvin to Celsius would be subtracting. And you end up with 244, a negative 244 degrees Celsius. Make sure you complete the other 2 as part of your homework. Now for pressure, pressure is a force exerted by a gas as it collides with an object. The actual calculations of pressure is force divided by area, but we won't be doing that in this class. There are several different scales to measure pressure. There's atmospheres, millimeters of mercury, torr, kilopascals. It depends on what situation for what pressure measurement you can take. Now, we need to know how to convert between these. Now, with temperature, it's adding and subtracting, but with pressure, these are ratios. 1 atm is equivalent to 760 millimeters of mercury. That means we're going to be using T-charts. Okay. Anytime you have a ratio, that's a T-chart. So if I have 2 ATM, ATM goes on bottom, millimeters of mercury goes on top, and I just plug in my numbers. For every 1 ATM, I have 760 millimeters of mercury. I won't plug them into my calculator for you, but you know how to do that. I'll also do E with you. If I have 92 kPa, kPa goes on bottom, millimeters of mercury goes on top, and I just plug in my numbers. 101.3 kPa per 760 millimeters of mercury. Solve with it in your calculator. The last vocab words you're going to need to be familiar with for this unit are standard temperature and pressure, which we've discussed before, but make sure you have these memorized: 0 degrees Celsius and 1 atm. Volume, which is the numerical amount of space occupied by a solid, liquid, or a gas. Hopefully you know this already. And then for moles of gas, we're going to be using this little symbol, lowercase n, whenever we do our calculations with it. We will not be doing just stoichiometry. We'll be using algebraic equations as well. Your homework for the weekend was to finish the temperature and the pressure conversions. And then if you flip to page 2, you need to summarize in your own words those 5 postulates for the kinetic molecular theory. I hope this helped, and I'll see you on Monday.